Welcome to Algae Prep Academy. The lesson for today is finding intervals of concavity using the second derivative test. Concavity is which direction the graph is opening towards. A function is concave down when its second derivative is less than 0. A function is concave up when its second derivative is greater than 0. The first problem is f of x is equal to x cubed plus 4x minus 5. The first step to approaching this problem is to take the first derivative, then the second. We're using the second derivative test to determine concavity. Use the power rule, bring down the power, subtract 1 from the power to derive. The next step is to find when f double prime is equal to 0 or undefined. This will give us the critical numbers where possible points of inflection occur. F is never undefined in this case because polynomials are continuous. Next, we'll make a number line of f double prime. This will help us illustrate where f double prime is positive or negative, as well as where critical numbers are. After, we'll use test points to determine where f double prime of x is positive or negative on the interval. From this, we can determine concavity. In this case, f is concave down on the interval negative infinity to 0, since f double prime is less than 0 in that interval. F is also concave up on the interval 0 to infinity, since f double prime is greater than 0.
Next, we're going to find the intervals of concavity of the function f of x equals x to the fifth minus 3x plus 3 all over x squared on the interval negative 5 to 5. First, we're going to take the first derivative using the quotient rule, then simplify. Using the quotient rule, we get f prime of x equals 3x to the fifth plus 3x minus 6th all over x cubed. Next, we're going to take the second derivative, again using the quotient rule and then simplifying. This gives us f double prime of x equals 6x to the fifth minus 6x plus 18 all over x to the fourth, which we can simplify to 6 times the quantity of x to the fifth minus x plus 3 all over x to the fourth. Next, we're going to find the critical numbers, or where f double prime equals 0 or is undefined. These critical numbers mark possible points of inflection, or where concavity may change. First, we set f double prime equal to 0. Since this is a fraction, only the numerator needs to be equal to 0. This lets us get rid of x to the fourth. Then we can divide both sides by 6 to get x to the fifth minus x plus 3 equals 0. We can then plug this into our calculator to find that x equals negative 1.341. Next, we need to find when f double prime is undefined. Fraction is undefined when its denominator is equal to 0. We set x to the fourth equal to 0 and solve for x. This gives us x equals 0. Next, we need to plot these numbers on the f double prime number line and test values between these critical numbers. This helps us visualize the concavity of f. The test points we're going to use are x equals -2, x equals -1 and x equals 1. Solving for f double prime of -2 gives us -81/8. Solving for f double prime of -1 gives us +18. And solving f double prime of 1 also gives us +18. We can use these test points to show where the second derivative is positive or negative. In this case, the second derivative is negative on the interval -5 to -1.341, positive from -1.341 to 0, and then positive again from 0 to 5. Therefore, f is concave down on -5 to -1.341, since f double prime is less than 0. F is concave up on the intervals -1.341 to 0 and 0 to 5, since f double prime is greater than 0. 5 is included in this interval since f double prime of 5 does not equal 0 and is not undefined. Note that x equals -1.341 and x equals 0 are not included on these intervals. This is because f double prime is neither positive nor negative at both of these x values. Next, we're going to find the intervals of concavity using the second derivative test of the function f of x equals sin x times cosine x on the interval 0 to 2 pi. First, we're going to take the first derivative using the product rule. This gives us f prime of x equals -sin squared x plus cosine squared x. Next, we're going to find the second derivative using the chain rule. This gives us -4 cosine x times sin x. Now we need to find the critical numbers, or where f double prime equals 0 or is undefined. Since f double prime only has simple trig functions, f double prime is never undefined. Therefore, we only need to solve for where f double prime equals 0. So we set f double prime equal to 0 and solve for x. Since the product of a number and 0 equals 0, we can just find where sin x equals 0 and where cosine x equals 0. This occurs at x equals pi n and x equals pi n plus pi halves, where n is an integer. Next, we're going to plot these critical numbers on a number line and use test values to find where f double prime is positive or negative. For our first test value, we're going to use pi fourths. Putting this into f double prime gives us -2. That means from 0 to pi halves, f double prime is negative. Next, we're going to use 3 pi fourths as a test point. This gives us +2, which means from pi halves to pi, f double prime is positive. For our next test point, we're going to use 5 pi fourths, which gives us -2, which means from pi to 3 pi halves, f double prime is negative. For our final test point, we're using 7 pi over 4, which gives us 2, which means from 3 pi over 2 to 2 pi, f double prime is positive. Now we fill in our number line accordingly, which helps us visualize the concavity of f. Looking at our number line, we know that f is concave down on the interval 0 to pi halves and pi to 3 pi halves, because f double prime is less than 0. F is concave up on the interval pi halves to pi and 3 pi halves over 2 to 2 pi, since f double prime is greater than 0. The endpoints of the intervals are excluded because f double prime is equal to 0 at each of these endpoints.
Thank you for watching Algeomulus Prep Academy. Don't forget to like and subscribe. Goodbye.
See ya!